Hey guys, welcome back to another episode. Today we're going to talk about something super important to physicists: eigenvectors. So let's draw an xy axis with 2 points on the axis, point A and point B. Point A will be in position -2, -2, while point B will be in position 2, 2. Now clearly we can draw an arrow from point A to point B indicating in which direction and how far we need to move in order to get to point B from point A. And this information can be held in a two-dimensional vector of 4, 4, indicating we need to move 4 points to the right and 4 points up in order to get to point B. These vectors hold a lot of information for physicists because they tell both the magnitude and direction of any given movement. Now, let's take a step back and talk about something else: transformation matrices, which are ways in which we may manipulate vectors into something entirely new. This is done by basic matrix multiplication. So let's take an arbitrary matrix, let's say 1, 2, 0, 2, 1, 0, 0, 0, -3. And let's take an arbitrary vector of, let's say, 1, 1, 1. If we multiply the matrix by the vector, we'll receive the vector 3, 3, -3, which is not necessarily related at all to the vector we put in, of 1, 1, 1. However, let's take another vector of, let's say, 1, 1, 0. After matrix multiplication, we find the vector 3, 3, 0, which is just 3 times the vector of 1, 1, 0 that we started with. In this way, you can see that after matrix multiplication, we get the same vector out with some sort of scalar value being multiplied by it. This particular vector is known as an eigenvector, and the number 3, the scale value, is the eigenvalue. In general, eigenvectors are any vectors which satisfy the following equation: sum given matrix A times V equals lambda V, where V is the eigenvector and lambda is the eigenvalue. In this way, after matrix multiplication, we get the same vector out that we started with some sort of scalar value, lambda. Now, that helps us understand things more mathematically, but what if we want to understand them more physically? Well, let's imagine we have some sort of three-dimensional cube in space completely filled with points. And let's take a transformation matrix and multiply it by every single vector in the cube. After matrix multiplication, you'll see that the cube has become something entirely new. Now let's watch that transformation one more time, except this time, we're going to draw a line between each individual point and all of its nearest neighbors, so we have some sort of three-dimensional grid in space. During this transformation, see if you can find particular lines that only stretch and do not at all change direction. Those lines that do not change direction are eigenvectors, and to really drill this point home, let's take 2 arbitrary points in space and transform them. You'll see that these 2 points in space move around all over the place, but if we take a separate pair of points that are along an eigenvector, you'll see that these 2 only stretch. I suppose this is even more obvious if we plot all 3 eigenvectors of this particular matrix during the transformation, along with a random pair of points. The random pair of points is clearly moving around all about, while the eigenvectors are moving just in and out. And that is an eigenvector in a nutshell. A vector that after transformation has not changed at all, except by a scalar value known as the eigenvalue.